Dear colleagues, my name is Ruslan Mokaev. I am from St. Petersburg University, and let me present our lecture, Harmonic Balance Method, Tsypkin Locus, and LPRS, Comparison and Counterexamples. The problems of the limiting dynamic regimes studying are associated with various classical theoretical and practical problems. One of the first such problems was related to the theory of regulation, which required the presence of an operating regime corresponding to a stable equilibrium state. An example of the mathematical formulation and solution of such problems is Vishnegradsky's famous work on the Watt regulator, where for a nonlinear dynamic model of the regulator, linearization in the vicinity of the equilibrium state were analyzed and conditions for its local stability were obtained. However, mechanical and engineering models were soon described in which stable periodic oscillations appeared, so-called limit cycles. Systematic study of limit cycles and their appearance in applied dynamical systems were carried out in the works of Andronov. He related Lyapunov's ideas of local stability analysis and Poincare's concept of limit cycles with problems in analysis of discontinuous engineering models, which resulted in development of the theory of oscillations. In 2009, Leonov and Kuznetsov proposed a new classification of oscillations, which reflected the engineering approach to the analysis of oscillations emergence and became a catalyst for the discovery of new oscillations in known systems. The oscillation is called a self-excited oscillation if its basin of attractions intersects with a small neighborhood of an equilibrium. Otherwise, it is called a hidden oscillation. One of the first general methods for analysis of periodic oscillations and global stability was the harmonic balance method, which originated from the works of van der Pol, Krylov, and Bogolyubov. The harmonic balance method is an approximate method for analysis of periodic oscillations, and therefore, in some cases, it may give incorrect results. The classical harmonic balance method was further developed and extended in various studies. For instance, a method introduced by Leonov and Kuznetsov allowed one to obtain initial data of stable periodic oscillations for a particular class of Fourier systems. Let us now consider the extensions of the classical harmonic balance method for relay systems, namely the Tsypkin method and the locus of a perturbed relay system method. These methods were developed in the works of Tsypkin and Boiko respectively. As it will be shown later, these methods yield more accurate results on predictions of the loss of stability and existence of oscillations compared to the harmonic balance method that may not show potential existence of an oscillations at all. Moreover, it can be shown that it is possible to obtain initial data for visualization of periodic oscillations. To illustrate the difficulties in analysis of oscillations, we consider the Keldysh model of flutter suppression by hydraulic damper with 2 degrees of freedom. In 1944, he published a paper where he used the harmonic balance method to analyze the emergence of oscillations and estimate the boundaries of global stability. Wherein Keldysh understood that he was using an approximate method and the results are not mathematically rigorous. To illustrate the problems in analysis of oscillations using the harmonic balance method, we considered Keldysh model with the following values of parameters. According to the harmonic balance method, there is one unstable symmetric periodic oscillation. But according to the Tsypkin and the LPRS method, there exist 2 unstable symmetric periodic oscillations. However, the Tsypkin and the LPRS methods also have limitations. To illustrate these limitations, let's consider the same values of parameters and using numerical modeling from the vicinity of the rest segment, it is possible to localize 2 self-excited limit cycles, and these oscillations cannot be found using the Tsypkin and the LPRS methods. Further, we considered the other values of parameters for this model. According to the harmonic balance method, there are no periodic oscillations. But according to the Tsypkin and the LPRS methods, there exists one stable symmetric periodic oscillation. And as for the previous parameters, we can apply numerical analysis and obtain initial data of 3 hidden periodic oscillations. One is asymmetric and the others are symmetric. And finally, considering the following values of parameters and applying numerical analysis, it is possible to visualize chaotic oscillation, which cannot be found using the harmonic balance method, the Tsypkin method, or the LPRS method. An interesting connection can be observed between these methods and the famous Eisenman and Kalman conjectures on global stability, which are as follows. Suppose all the following linear systems are asymptotically stable. Then all nonlinear systems with particular conditions on nonlinearity function are globally stable. According to the harmonic balance method, these conjectures are true, but multiple counterexamples were constructed. We can also construct counterexample to the Kalman conjecture by performing numerical continuation procedure of the Keldysh model. As a result, we obtain a system that satisfies conditions of Kalman conjecture, which has stable equilibrium state coexisting with 2 periodic oscillations and 1 chaotic oscillation in its phase space. So, difficulties in analysis of oscillations in Luria systems with one scalar nonlinearity are connected with the problems of localizations of hidden oscillations and possible birth of chaotic regimes. Also, analysis of the Keldysh model demonstrates the advantages and limitations of the harmonic balance method, the Tsypkin method, and the LPRS method. The harmonic balance method may not predict existing oscillations. Also, the Tsypkin method and the LPRS method are able to find symmetric periodic solutions with exactly 2 relay switches per period. Therefore, they are unable to find both asymmetric solutions and solutions with a higher number of relay switches. And these oscillations may be self-excited or hidden. And all these methods cannot find chaotic oscillations by design. Results of our research may be used for the further development of the Tsypkin method and the LPRS method. And finally, localizations of hidden oscillations allows one to estimate the outer boundary of global stability. Results of our research are presented in the following papers. Thank you.